Okay, the brave ones stay. Let's talk a little bit about software protection and what is this software protection. Alfonso got me involved. He told me, come and tell me your stuff. And I like cryptography a lot. I am very geeky, but I do not do it in general. I don't investigate cryptography. It is true that in much of what I do, I end up reading papers by Mr. Rivers, Mr. Shamir, because they have investigated many things that are useful to me. So in the end, I said, well, why not? Let's do some cryptography. Well, I'm Arnau. I do a lot of things in a lot of places. I work in Activision. I do math in Activision. I do math in other places, and I reverse everything they throw at me. What's the context? Today, I'm a bit of a self-promoter because we don't have a lot of time. When we talk about software protection, we talk about protection techniques in a scenario that is known as mate or man at the end, which is a completely adversarial scenario. It's a scenario in which what we want to protect, the analyst looking at it is going to have total control over a copy of the program code, as well as the environment. And when I talk about environment, I'm talking about hardware. I'm talking about the operating system. He has control of that. And as you can see, there are a lot of protections that can be seen both at the legal level and at the technical level. At the legal level, we won't comment on anything, but at the technical level, we have, you see, trust native code, execution at the server level, encryption, of course, cryptography, and obfuscation. And I'm going to focus again on obfuscation, which is what I mostly do, but now we're going to see how to apply it to cryptography a little bit. Cryptography a little bit. What is obfuscation? Very quickly, obfuscation is simply take an input program, a piece of input code. We are going to transform it so that we get another output program from P to P. And this output program has to be functionally equivalent, semantically equivalent. That is, it has to behave the same as the input one. What we want is that it verifies certain properties. These properties are mainly that it has to be more complicated to analyze and more complicated to extract information. And when I say more complicated to analyze and extract information, I mean both from the point of view of the analyst who is dealing with it and from the point of view of the tools. And when I say tools, I mean disassemblers, compilers, debuggers, binary instrumentation, and whatever you think is necessary for any process. This is reverse engineering in general. The motivation? To prevent reverse engineering. Here, if there is someone reverse engineering or protecting their software, you know that this cannot be prevented. In an adversarial scenario, you can never prevent reverse engineering. What you can do is complicated, and in the end, in this game, is to make your adversary to have to spend more resources than he is willing to spend. If your opponent has infinite resources, unlimited time, he's going to beat you every time. Now, if you are able to set up protections such that your rate of protection is faster than the rate your adversary has to unprotected, then you've won the game. Where do we see obfuscation software protection in particular? In everything that is commercial software protection, intellectual property of algorithms, DRM in multimedia files mainly, and everything that has to do with cheating and anti-cheating. Also in malware, although I say it lately. Malware today is outdated. People who are bored with malware, there are technically much more interesting things. The obfuscations that are in malware and in DDR bypass and things like that are very good, and they are toys. So in malware, it's used to mainly to slow down time, that is to gain time or to gain money in campaigns. The longer a campaign is active, in general, the more money, which is what malware actors are looking for. What is the methodology? Very roughly, we are going to apply semantic transformations that preserve semantics. That is, that preserve behavior to both flow control and data control. In other words, what we are going to do is to take all the control structures, branching loops in the code, all the data flow structures, that is to say, what are the computational procedures by which a value ends up in a variable at a given time in a program? At what levels? Well, at source code levels, it can be done. In general, also at the intermediate representation level. I'm thinking mainly of LLVM. And also at the binary level, this is tricky because if you touch a binary, then you have to make it work. You will have to correct the header. If you have touched memory addresses or you have extended it, you will have to correct all the memory jumps, all the absolute relative addresses, etc., etc., etc. But you can do it. And if you can't ask your compiler to send you the assembler, obfuscate the assembler, and then ask the linker to give you the binary, it makes your life easier. And what do we obfuscate? Well, the whole program, functions, basic blocks, instructions. in general, the whole program, we do not attack it directly because basically to take a transformation where the input of the whole program can do little more than a very glorified packer. What you do if you want to obfuscate an entire program is to obfuscate all the functions, obfuscate all the basic blocks, or obfuscate all the instructions if you want. What is the obfuscation? Well, it's kind of the reverse in a way, or so we would like it to be. We start from a program that is obfuscated, which is complicated to extract information and analyze, and we are going to do a process that preserves the semantics, hopefully, and get a program that we are going to call P. And what we want is that the second program is easier to analyze, easier to extract information. As I said, we would like this P to be as close as possible to the initial P, but this usually can't be guaranteed in the first place, because if you're doing this in an adversarial scenario, it's because you don't have access to the deobfuscated code. That is, there is one only case where you do have access, which is when you do academic research, which you look at your methods and test whether it makes sense or not. But that is not the scenario where we are working now. But apart from that, in general, from the point of view of deobfuscation, of analyzing protected binaries, what we are interested in are very specific parts. And in general, we are not so much interested in reconstructing a working binary. We are interested in understanding what is going on, maybe re-implementing it, maybe, well, reverse it and make our own reverse algorithm, not so much rebuilding it. Okay, let's get right to it. This is my favorite thing in the world, the mixed expressions, Boolean and arithmetic. And I like it a lot because nobody does it and because it is very nice and it is not so complicated. In the end, we're going to use one of these expressions to obfuscate and to reason about code. They are simple expressions where the only thing that happens is that we mix arithmetic operators and logical operators in the same type of expression. There is nothing else. The trick here is, first of all, a little bit of notation reminder, because I'm going to use a little bit as much operation at the level of mathematical expressions as in code, and, or, XOR, and not, in case you see the notation around. The move is, what is a polynomial expression and why am I telling you this? I tell you this because it is going to be very important for you to see the transformation processes. Before, I used to put a little bit more formal definitions. Now the only thing I'm going to tell you is, if you know what a normal polynomial is, it is the same, but thinking the variables as Boolean expressions. This mixed Boolean and arithmetic polynomial expression, you can think it as a normal polynomial, where what we do is a remapping of variables, and our variables are now Boolean expressions. With this remapping that I propose here, our polynomial MBA is simply our multivariate polynomial normal arithmetic with this remapping. This is just to understand a little bit what it is about, how these expressions are constructed. Then there is a much simpler constraint, which are the linear ones, and then we will also see why I am interested in talking about them. The linear ones are a subset of the polynomials. That is to say, all the lines are polynomials, but what we do is that we are going to allow only one Boolean expression for each term. The polynomial at the end is a sum of terms. So for each term, we are only going to allow one Boolean expression. In a way, you can think of it, in this case, with this same remapping of variables, that it is something linear. When they talk to you about linearity, and in cryptography, they like to talk a lot about linear issues. Linear means that the variables don't multiply. And here, our variables are Boolean expressions, so we don't have Boolean expressions that multiply. This is important because when we have linear things, we can do linear algebra, which are matrices and vectors. And when we don't, well, we have a problem, or we do algebraic geometry, which we're not going to talk about, but we can do little things. And here I am going to say this, and I am not going to justify it too much, just a little bit, because otherwise I will eat all the time. The software protections, the state of the art, in principle try to use this type of transformations that mix these two types of operators to merge code. And I say they try, because they do it very badly in general, and then we'll talk a little bit. Why do they do this? Well, mainly because when you combine these two types of operators, because we are ignorant, we do not know very well what happens. Here I say that they do not interact very well together. What does it mean? Well, we don't have rules or general theory to deal with it, and then we don't have software to deal with it. Try to put mathematics, HMAT, or any computer algebra system expressions with mixed operators, and good luck. At best, they will support Boolean expressions in isolation, no way mixed with arithmetic, no way symbolic. Where can we represent these expressions? With SMT solvers. The problem here is that, without getting too much into the rag, SMT solvers are in theory quite good for testing semantic equivalences, i.e., I give you two expressions. See if they are equivalent, i.e., if they produce for all inputs the same output. What this can be, we can skip it very easily, deliberately, with MBA transformations. When we introduce MBA transformations with an algebraic degree of 2 or more, i.e. which are not linear, the SMT dies. And besides, the problem of verifying the semantic equivalence between the two expressions is a different problem from the problem of I have a very complicated expression, I want to get a simpler expression. They are two different problems, which sometimes I also come across a lot of papers that confuse these two problems, and they are talking about one thing when they refer to the other. They are two different problems. How do we search for expressions? Very quickly, there are a couple of main techniques. The first is, well, we take an operator and we rewrite it. We do a rewrite with a rule that gives us another expression that mixes polemic and arithmetic operators and allows us to translate an operator, in this case a sum, into something a little bit more complex. These expressions are easy to generate, and when I say that they are easy to generate, it is because they are linear. And it means this. We are not going to go into how to do it, but there is a constructive method that is well known, which is to set up a matrix, solve a system of linear equations, and get some coefficients for the rewriting rule. And I put easy in italics because absolutely nobody does it. Everybody copies and pastes from a couple of published ones. But, well, it's easy to generate. You read the algorithm, implement it, and that's it. These rewrite rules, and here is why I have told you the polynomials and I do not know what, can be applied iteratively. And they can be applied iteratively because polynomial mixed expressions are composable. What does this mean that they are composable for those of you who are not very deep in this jargon? It means that if I have 3 expressions, for example, these 3, whatever, I can take 2 of them and use them as inputs for one of them. I can use as inputs not only variables, but expressions themselves. You can see this in many ways. Here I have put a couple of more visual examples. The first is you can see it as a consecutive application of the rewrite rule with a change of intermediate variables. And this sounds really weird, but it's nothing more than I start with the addition, I do the first rewrite. Now that I have the rewrite rule, I do the left summing to the right. So I say, what is on the left I call x, what is on the right I call y, and I apply the same rewrite rule to x and to y. I undo the change of variables, I get the expression, I have another sum, I call it x, yeah, and so you can go on until you get tired. You can also see another way of looking at it is that the rewrite rules apply at the level of the abstract syntax tree representation. That is, if we have a sum, for example, this sum represented as a tree, I can apply a rewrite rule to an operator to everything to the left of the tree and everything to the right of the tree, starting from the operator. Here, what is on the left is the x and the y. I apply the rewrite rule, and here, notice that I have a sum at the top, everything on the left and everything on the right. I pack it left-right and apply the rewrite rule to everything on the left and everything on the right. It's another way of looking at exactly the same thing. And you can generate as much as you want. You're taking left-right, you pack it, the change of variables, and you can rewrite. This is just to tell you that you can go as far as you want. You can iterate this as far as you want, and with very little rewrite rule, you can do whatever you want. Then this just makes us linear. We want to put in degree, or we would like to do other transformations. How do you do that? By putting in identities. Identities, I simply take a pair of functions that are inverses of each other. That is, if I apply one and then the other, they cancel. And I simply apply them one after the other to the expression, and you will say to me, man, if they cancel each other, then nothing happens. No, they cancel semantically, and you get something more complicated. For example, I give you this expression, which is the same as the one we have seen. This pair of functions are inverse functions in 8 bits. And nothing, we write it. We just write it down. We put E inside F, apply the function, apply fem1 to FD, write it out, and we get something bigger. This can be used with affine functions normally. Almost always affine functions are used for something that if I have time at the end, I will comment a little bit. But you can use permutation polynomials of arbitrary degree. You can use any inverse mapping that you can imagine, but they are not so easy to generate. And if you are into cryptography, you might be familiar with T-functions, which are mappings that are known to have inverses, although I don't know how to find them. But if you know some method to find them, then use them too. We can also obfuscate constants with this very simple method. We have a constant that we want to obfuscate. We take a pair of, usually here in this case, permutation polynomials. Again, any pair of inverse functions will do. And we take an MBA that is non-trivially equal to 0. That is 0. That is, it evaluates to 0 for any input. What we're going to do is replace our constant with a computational procedure that computes the constant for us. Okay? So it always computes this constant. How do we do this? Well, we simply apply some polynomials to what's inside, which is the sum of the MBA to this null plus the other polynomial to the constant. This can seem a little taken out of the sleeve, and I'm not going to demonstrate it to you because I'm going to demonstrate it without formal. It is a little technical, but morally it is very simple. If you think about the semantics of what's inside the application of P, you have a semantics of something that is 0 and the semantics of the polynomial Q. So the semantics of E, which is 0, is kind of vanishing. What you're left with semantically is P of Q of K. But P of Q are inverses, so you're left with K. Okay? That's the moral intuition of why this works. The proof is a little bit more technical, but it's this idea. Example, a constant in 8 bits, 2 permutation polynomials of degree 2 in 8 bits. This MBA that you see here, the E of X and Y, is an MBA that if you put in X and Y will always give you 0. We do the procedure and we get this expression. This expression is an expression that will always compute the constant of 123 in 8 bits. You can choose so many combinations of these MBAs that you can generate and permutation polynomials or any kind of inverse function and generate whatever you want. We are going to use this for cryptography because in the end this is a crypto suit and I had to get some crypto in there, and I've come up with quite a few things actually. First, a couple of little words of differences when we deal with mixed operators in obfuscation and in cryptography. In obfuscation, what we're looking for is we have an initial expression. We're going to generate a second expression that is syntactically much more complex. Syntactically means the way it is written. But this expression has to preserve the semantic component. It has to preserve the behavior. That is to say, we generate a syntactically very complex expression, which is written in a very complex way, but which preserves the semantic component because it does the same thing. The behavior is the same. It is very simple. In cryptography, not exactly. To begin with, cryptographers don't talk about MVAs. MVAs is a thing that has been invented by people who do software protection at the term level. But they use them, even if they don't give it that name, because as long as you're mixing operators, you're using this. The issue with cryptography is that when you mix these operators, what you are looking for is a little bit the opposite. You want to generate complicated semantic behavior. You want your crypto system that you are making by mixing arithmetic and logical operators to fulfill certain properties. I'm talking about nonlinearity. I'm talking about a high algebraic degree. I'm talking about you have to guarantee these crypto buzzwords that are the diffusions of confusion. So you use mixtures of operators to guarantee this. The summary is this. In obfuscation, we have a complex syntax related to a simple semantics. That is a complex way of writing for a simple behavior. In cryptography, the way of writing is complex precisely to look for a complex semantics, a complex behavior. A complex semantics, a complex behavior. That you cannot reverse any hashing algorithm, or you can take out the inverse of A is in the key, things like that. Okay, I have a little bit of time, but I think I'm going to go for it. Crypto hardening ideas with obfuscation with this. First, before anyone goes for the jugular, of course, when we obfuscate to whatever cryptography is, whatever it is, there's a trade-off in performance. Absolutely. If we're putting in more operations at more hops, well, performance is going to suffer. The question is to be very smart about how we do it, where we do it, and what features we have, how far we can do it, and what characteristics we have, how far we can stretch or not, depending on the context. We'll talk a little bit about this. One idea that occurs to me very simply is like, well, we're going to hide computations that can be recognized in cryptographic algorithms directly. What we want is that the analyst, again, almost reverse engineering, who has to fight with a bug or any protected program, that it's not easy for him to recognize patterns that are very well known by classical cryptographic algorithms, looking at the assembler or looking at the source code or the compiled code. The method is very simple. So we take these operations that are known and we obfuscate them with operator transformations, with rewrite rules, with the identities. And there is a type here. Well, if you have a transformation that's applied a bunch of times in a loop, every time you enter the loop, make it a different transformation. You can generate as many as you want. For example, a SHA-256 implementation of Linux core utils. Here you have some defines with some macros, and then here what you have is the SHA-256 compression loop. I'm not interested in whether you know this or not. What interests me is that there are some mixed operations, good and arithmetic, both above and below. So I can take, for example, the first of them all and say, well, this define, this macro, I'm going to obfuscate it. How? Well, I'm going to rewrite it as far as you want. And the same with the operation that was inside the loop. So in the end, it is a sum of 5 terms. Well, in addition, we have the goodness that they are associative. So I can say this is a sum of 3 plus a sum of 2. So I am going to apply the rules of sums as far as you want. And all this is the Same thing, semantically. It does exactly the same. In fact, when you have the slide, you can check it out. So this does exactly the same thing. Another little thing. This for people who make malware or who analyze malware more than they do, or there you go, is finding constants. That is to say, those of you who have fought with malware, how do you find cryptography in malware? Well, you go to find crypto, your Yara rules, and you say, find me known algorithm constants. You go to the constant, you look for the cross-reference, and you say, it's used here, this is an MD5, this is a I don't know what. Well, you don't have the constants, so you don't find it like that. How do you do it? Very simple. You replace these constants by computational constructive methods that construct them in runtime. And well, what I was telling you before, you can build as many as you want, because if you use a constant 25 times, you can have 25 different computations that produce the same constant, each one different, and then generate the grandparent if you want to dynamically with a little bit of cunning. Constants that you can attack, well, some ideas. The initial variables of MDV, the ASS box variables, or whatever you can think of. Any type of constant in cryptographic algorithms, you can substitute. Normally these are in lookup tables that you are going to look at. Substitute this by an obfuscated computational process as many times as you want that give you the constants in runtime. Then you don't find them anymore. Of course, this can be combined with the technique from before. So combine everything with everything. White box cryptography. White box cryptography, maybe some of you are familiar with it. And it's used quite a lot, although there's a bit of secrecy with this. I don't know why. But the point is that we must prevent that embedded keys can be extracted. I have to give a product or a software or a hardware that needs a key that is in there. And think about, I've been a DVD player for 1,000 years. Any DRM thing, when you have Netflix and you download the content to watch it offline, this is encrypted, and then it has to be decrypted and you're offline, so it needs the key somewhere. So it's this kind of scenario. What's going on here? What is the method of white box cryptography is called? What you do is mix together, that is the procedure, the crypto system, which normally would have as inputs the input that you want to decrypt and the key. Now as input, what you do is an ad hoc implementation. That implementation itself has no input from the key, but in its computation as such, it is computing the same result as if it had a concrete key. The idea is, in a standard implementation, you have as input your input and the key to encrypt or decrypt, and it gives you the output. In white box crypto, what you do is you simply have an input. You generate an ad hoc implementation that will generate all the computational process. It will give you the same output as if you had encrypted with a key, but the key is nowhere. It is embedded and mixed within the process itself. And what do MBAs do here? Well, as far as I know, there is no process as very standard to generate white box crypto, but I can assure you that with MBAs you can make white box crypto because, well, a key is nothing more than a root of bytes. Each byte is a constant. Well, you can pull the thread and obfuscate constants, like at the level of arbitrary computations, then you can pull the thread and build this fairly easily, relatively easy. Some conclusions. First, context matters a lot. Context matters a lot. Who is your adversary? What capabilities does he have? And what capabilities do you have? What do you need to protect? I mean, do you need to protect algorithms, constants, keys, everything? And here I was saying, how much can you afford in terms of computational cost? Computational cost, and this again depends on the context. For each asset you want to protect, and where do you want to protect it? It is not the same. And now I am talking about an example of video games that is very easy to understand. It is not the same that you want to protect a function that runs every time you start a game every half hour, that loads the textures, defragments them, whatever, than a function that is going to be executed every time a frame is rendered on screen up to 240 times per second. It's not the same, and you don't have the same limits. So you have to be a little bit smart here. And in order to be smart here, you have to have the ingredients and know how to use them. Then more conclusions. The mixed algebra, these transformations are quite powerful and not too many people know them. And the people who supposedly know them, I don't think they know them too well from the way I've seen them used. And as of today, virtually no commercial product that I have seen uses them correctly. And when I say they use them, they have no idea what they are doing. They copy and paste some rules they've found out there and run. then they just use linear rules, literally copied and pasted from two very specific resources. One is the Hacker's Delight book that has a part of bit hacks. There are 4 or 5 of these rules. And another is a thesis of a French girl who talked about MMBAs and had an appendix with a few rules. Well, these rules serve you to deobfuscate everything obfuscated with commercial protectors. And that's it. And I'm surprised because these products are worth many thousands of dollars a month in licenses, and they haven't read the algorithm and implemented it. And then the identity issue is when we put in inverse functions, almost all of them are affine. And again, it's a little bit, they are affines because the initial paper where this is presented says that we are going to use affines, and everybody uses affines. But as long as I have an inverse map, I don't care what it is. It is true that affines are very easy to calculate. They are inverse. The permutation polymorphs can be calculated with the inverse of a restricted set quite easily. There are ways to do it in general, but you can't do it anymore. You know, people just don't implement it. And then we can protect cryptographic implementations with these transformations. We've seen algorithms, constants, keys, and a little bit whatever you can think of. And this morning at the hotel, before I came here, I thought of something and I said, I have to stop and write it down because I have to tell you about it. And I called a friend of mine who does side channel and I asked her, does this make sense? And she said, I think it does. So I'll tell you about it and I'll leave it there. It's a little bit of a crazy idea that I came up with. If you want, we'll talk about it. I mean, well, if we have control over the syntactic complexity of the operations, we have some control over the timing of the operations. I can control to some extent what is the execution time of each operation that I'm fusing. So I can manipulate the duration of certain cryptographic operations within the algorithms. And I can do it dynamically because I can generate these dynamic transformations. If I want in runtime, each time I generate a different one with a different length, with different tenacities, that I can control the timing of each one of them. Therefore, I can also make it dynamic from, well, I do not have to put in this sum, this kind of transformation. Every time it runs, every time there's a trace or every minute, I change the type of transformation to give me a different timing. And if you pull the thread a little bit with this, because what you are setting up is a thing that I invented this morning. I give it this nice name that is timing-based side channel honeypots. So you set up systems where it looks like there are side channels, but good luck, they have to fight picking up traces because it changes dynamically. If the timing information you get is not consistent, and you're going to think your trace pulling machine doesn't work, and you're going to be there, well, fighting with something that's not a side channel. What you have is deliberate timing information that changes however you want it to change, because you can build it however you want. Dynamic, changing it every trace, every minute. So, well, I'll write something about this at some point if I see that it makes sense. And if anyone thinks this doesn't make any kind of sense, let me know. It just occurred to me this morning. And nothing, not much more. Okay, I don't have time anymore. So, well, last slide. It's very fast. I have a training where I talk about these things and many more. Obfuscation and deobfuscation. I do it over there. Public, private, in-person, remote. You have details there. You can contact me. If you're not going to be in Las Vegas or Thailand this summer for one of these events, well, I'll be there giving it in person in case you're interested. And little else. Thank you very much. The truth is that it was a short talk, but I think it was interesting. And I wanted to see how I could apply a bit of cryptography and these ideas to my research. And I'm happy to talk with you because it's a little bit out of my hands to see how it can be used. And some things make more sense than others. But hey, thank you very much. Any questions? Already? Hi. Let's see, this last topic is really cool and I'm interested in it, right? This Team Viceit thing, I mean, since you're going to get into it, it would be cool if, for example, right, I'm with manufacturers that are using hardware vulnerable to fall injection and everything, right? So with these kind of things, if you implement in the password check, any kind of validation, a library that they can take and dynamically change everything, you tell them. Instead of, it's from Brian Glassman in C, that he uses everything, you know, which ones, right? In this case, it's very typical. Instead of Brian Glassman's, I take this one and it's dynamic everything. And even if you have a crappy hardware that you should not use in automotive, well, you get rid of the attack, right? Are you going to do something like that in dynamic implementations that I can copy and paste and not think, I don't know, I guess I'll see. I mean, it occurred to me this morning, I mean, I'm not kidding. It occurred to me this morning. I want it. I'm going to see if it makes sense. I told you it occurred to me this morning. I called a colleague and I said, hey, does this make sense? And she said, I think it does. I say, well, I'm going to tell you. It's a great idea. I'll look at it. Well, we'll look at it. Can I ask the audience a question? Who didn't know what MBAs were? Can I have a show of hands, please? Okay, cool. I know it's hard at 7 o'clock in the evening today, polynomial, right? As a concept, but if you ever have to protect anything, this is the solution. Or, yeah, it is. One of them, yeah, it's one. Any more quick questions? If we go to the last lecture. Come on, two. No, they go that way later. I think so. I really enjoyed the talk. It was very interesting. Something I've read about. Do you think MBAs are limited by the compiler's capacity? After all, you, in mathematical theory, you are over an infinite set of numbers that you can apply to the MBA. But here we run into constraints at the register size level or in memory. Okay? Yes, very fast. I use MBAs not on abstract mathematical structure. I use them on bit vector, that is on rings, dense, modulus, 2 to the n. That is the same thing you use, the same register size, memory locations. 64-bit values or 32-bit values or 16-bit values, whatever you want. So this is where the weak point comes in then, that current MBA deobfuscation tools apply. Well, it's that the current MBA deobfuscation tools, there are so many approaches that we could go on and on. What is more advanced is to use the linear ones, because in the end, with the linear ones, you do a little bit of magic with linear algebra, and you can get things out of them. Then, for some linear, not for all, and then with synthesis. That is, I take the expression, I treat it as a black box, I throw inputs, I collect outputs, and I synthesize in some way. There are many techniques, some better than others. What happens? This works in quotation marks, because as soon as you put, and we are not going to go into it too much, but as soon as you put a constant inside one of the Boolean expressions, it crashes. As soon as you put a high algebraic degree, it crashes. And the way to deal with this is with algebraic geometry, which we'll talk about some other day. Okay, thank you. One last one real quick left over there. I'll get it. Hi, yeah. I was going to ask a question, but I don't know if it's going to be complicated to ask the question without a pen and paper. Well, you shoot. If not, we'll look at it later. The classic trick of making a swap of two variables using an XOR or a sum can be rewritten as roots of the identity matrix. And it can be written either in a GF space 2 of these or in finite body, in any kind of finite body. And they can be written as, I mean, you can take identity roots of several of these bodies and combine them as mm to the minus 1. You know what I'm saying? Yeah. Separate the inverses of 1 with the inverse of 1 and combine it and do something like algebraic expressions. Yeah, you can do that. You can do that. It just reminded me of that, and you could combine that technique with this one. No, it doesn't exactly ask. Well, no. But in the end, this gives you a background of, well, you can decompose a matrix identity, as you put it, the product of roots. And this, well, I don't deal in general. Let's see, a little bit technical. I don't deal here in finite bodies. I deal with tooth rings, which in the end are values of n bits, values of 6th and 4 bits, to understand us all, or 32, whatever. But yes, you can do it without getting stuck. That is to say, with bit vectors, once you have done this, if you want, you can obfuscate it more. You have an expression at the end that you can obfuscate with all the techniques you want. You can combine it, yes, without any problem. Well, nothing else. Choose. The radio for who? To the radio for the second guy, which Drek has a lot of. A shell for Drek. Someone gets a shell. Well, thanks for coming, Arnau. A big round of applause to you. Let's go to the last talk of the day with Javier. I know I'm competing with all the Tarlogic beer, okay? But hang in there. It's quick, okay? 25 minutes and that's it. And the talk is very good, Javier's talk. Well, do you sit down? Hell no.